Hello students, welcome to this part 5 of the module on linear algebra. In this module we are going to discuss determinants, inverse and rank of a matrix. Remember that in the last lecture, the last module, we discussed the notion of a matrix as the representation of a linear operator in a given basis. If I take a linear transformation y equals ax, okay, where a is a linear operator, right? Now if you represent this in a given orthonormal basis, then we got something like yi is aik xk, okay. So if you write in conventional notation, so you can write y as a column vector, so on up to n. I'm assuming the space to be n dimensional, okay. So you will have a11, a12, a1n, similarly all the way up to an1, an2, ann, operating on or multiplying the column vector that represents the vector x. Okay, I'm sorry about this. This is n. Okay. Now this object is a matrix. This is specifically a n by n matrix. Okay, so now this linear operator, when expressed in a given basis, takes the form of a matrix aij. Okay, now you can ask the question, what happens to this components of this matrix a11, a1n, an1 and so on up to ann? Do the components remain the same if you change the basis? No. The components change in general if the basis is changed, right? Just as if you have a vector, okay, if I change the basis, then the individual numbers will change. Sorry about this, right? But that's the same vector which has different representations in different bases. In the same way, the matrix also, the elements of a matrix, the numbers that represent the elements of a matrix will in general be different in different bases. Now you can ask the question, are there some combinations of the matrix elements that remain unchanged, or in mathematics people use the word invariant, under coordinate transformation? You can ask this question. In general, of course, these entries, as I told you, these entries a11, a12, a1n, and all these entries will change. The numbers that represent these entries will change if you change the basis. Now, are there some combinations of this matrix elements which remain invariant under coordinate transformation? The answer is yes, and one of those invariants is the trace of a matrix, which we saw in the last lecture. The trace of a matrix is simply the summation of all the diagonal elements of a matrix. Okay, this is an invariant. Trace is an invariant. The other invariant that we are going to discuss today is the determinant of a matrix. Okay, we will later on see that you might you might have heard of the term eigenvalues of a matrix. Eigenvalues also remain invariant under coordinate transformations. We'll come to that a bit later. But right now, in this module, I'm going to discuss a little bit about determinants. Okay. Now, a determinant, of course, is a single scalar number like a trace that comes out of a matrix. Can be real or complex. Okay. So this is a single scalar number that comes out of the matrix, the given matrix. Okay. A matrix in general is an n by n is So one important thing, both trace that we discussed last module and determinant are defined only for square matrices. That is, the number of rows should be equal to number of columns, n by n. You cannot have m by n or n by m. Okay, right. Now, so the determinant of A is denoted as det A, or simply this. Okay, this symbol is much it's used in different it has different meanings in different contexts. For example, we say this is modulus of -3. We can simply use this in real numbers. In complex numbers, we use this to represent absolute value of a complex number. In linear algebra, we use the same symbol to represent determinant. So you got to be careful while understanding this notation. Okay, so of course it changes from context to context. So here, of course, I will try to indicate a matrix with in my notation, a vector has a single underscore. A matrix will have a double underscore, right? So determinant of A is represented as, let's take a 3 by 3 matrix. Okay. Now, how do you calculate that scalar number? That's the point that we're going to discuss, right? Okay. In order to come up with an algorithm for calculating determinant of not just 2 by 2, 3 by 3 matrix, we are interested in a general definition of determinant of n by n matrices. Okay. So, in order to do that, we have to define two important terms and tell how to calculate them. These are called minors and cofactors. Okay. Okay. So now I have to take an example. Let's take a 3 by 3 matrix: A11, A12, A13, A21, A22, A33, A31, this is A23. Okay. The minor Mij of the element Aij is the determinant of the n minus 1 by n minus 1 matrix obtained by removing all the elements of, let me write down and then explain using this, obtained by removing all the elements of ith row and jth column. Okay, suppose I am interested in let's say M13, okay, just for the sake of argument. Now what am I supposed to do? Now I'll take the first row and third column, and then I will knock off all the elements. Okay, this is the first row. Okay, this is the first row. This is the third column. When I do this, I get this matrix. Okay, so what is minor M13? M13 M13 is the determinant of this matrix: A21, A22, A31, A32. Okay, now if you were to ask, okay, let me remove this first. Okay, now if you were to ask me what is the minor of M32, okay, what should I do now? Again, I will go to the third row and second column. So I'll first knock off the third row and then I will knock off the second column. So M32 will be the matrix that is obtained by calculating the determinant of A11. So I have knocked off these two, A13, A21, A23. Okay, and so on and so on, right? So I'm giving you two examples. So this is the notion of a minor. Okay, so let's take a new page. Now, what is a cofactor? Cofactor, Cij, of the ijth element of a matrix is nothing but minus 1 to the power I plus j times mij. Okay, so remember that mij is a determinant. A determinant is a scalar, right? So we'll come to how to find the determinant. See, in the previous I have only told you how to find M13 in terms of this determinant. I have not yet told you how to calculate this determinant. I'll come to that in a minute. Okay, so you do it in a recursive fashion, okay, step by step fashion. So what is the cofactor of A23, for example? That's nothing but minus 1 to the power 2 plus 3 times, I have to knock off the second row and third column. Okay, so if I knock off the second row, I'll have to consider the first row and the third column is knocked off, right? Second row is knocked off. Okay, so this is nothing but minus 1, because this is minus 1 to the 2 power 5, 2 plus 3 is 5, right? Okay, so this is the cofactor C23. Okay, now how do I find the determinant? I'll come to the expression for determinant of a matrix A shortly. Now how do I find the determinant of the 2 by 2 matrix that comes out, right? So to find A12, A13, A through 2, for example A33, we will end up with such determinants for each of the matrix elements, right? So we need to find a way of calculating the determinant of this, whatever, right? So that's what I'm going to tell you next. Now again we have to apply. Before I do this, let me tell the definition of determinant, and then I will tell you how to apply this recursively, right? The definition of determinant, the fundamental definition of determinant is the following. This is called the Laplace expansion. What is this? The determinant is the sum of the products of the elements of any row. You pick one row, any row, or column. You take either a row or a column, and there that is, you take any row and then take the elements of that row. Suppose I take the first row, right? Let's consider a 3 by 3 matrix. There are 3 elements. So I take each of these elements and then I multiply it by their cofactors and then add them up. So determinant of A, which is det A, is nothing but, in that manner, it is A11 C11 plus A12 C12 plus A13 C13. Okay, so we can also do this. Determinant of A is also equal to A21 C21 plus A22 C22 plus A23 C23, or I can also write it as A13 C13 plus A23 C23 plus A33 C33. I can take either a row or a column. Okay, it doesn't matter. I have to take the elements and multiply the cofactors of those elements in that given row. Okay, so this is what the determinant is. Suppose I take a 3 by 3 matrix. So there are many expressions for determinant, right? Depending on which row or column you choose, they all will give the same answer. Okay. So let's take a 3 by 3 matrix. One example of a determinant is what you typically do in your high school or earlier courses in mathematics. You will pick the first row, right? That's what you typically do. You will pick the first row, right? And once you pick the first row, you will say that A is equal to A11 times C11 plus A12 times C12 plus A13 times C13. Now let's write what is C11. What is C11? You have to neglect this row, sorry, this first column and first row, and minus 1 to the power 1 plus 1 times, determinant of A22, A23, A32, A33. Okay. Now what is C12? It is minus 1 to the 1 plus 2 times the determinant of. Now you have to delete this first row and second column, so you will get A21, A23, A31, A33, and then finally we have C13, which is minus 1 to the power 1 plus 3. Then you have to neglect the first row and third column, so you will get A21, A22, A31, A32. Okay. Now, how do I calculate these determinants, which are now determinants of 2 by 2 matrices? Well, let's do this. Show with an example. So, consider A12, A13, A32, for example, A33. Suppose I am interested in this determinant. Okay. Now, when you consider this determinant, you have to be very careful. Here, I have already arranged the matrix. This is the 1 1 element, this is the 1 2 element, this is the 1 3 element, and so on, right? So when I calculate the cofactors, the elements, A11 means I do 1 plus 1, A12 means I do 1 plus 2. But here I have to be careful. I have to first relabel this element as the 1 1 element of this matrix. This is the 1 2 element of this matrix. This is the 2 1 element. This is the 2 2 element. Okay. Once you do this, the determinant of this 2 by 2 matrix, the submatrix, is again the same idea. A12 times, I'll take the first row and then I'll take the cofactor, which is minus 1 to the power. The most important thing is you should not put 1 plus 2, it is 1 plus 1, because this is the 1 1th element of this matrix, times. Now we are left with only one number. There is no submatrix. It's a 1 by 1 matrix in some sense. So this is A33, determinant of A33. I'll tell you what is determinant of A33 in a minute. Plus A13 times minus 1 to the power 1 plus 2. It's not 1 plus 3 because now this is the 1/2 element of this submatrix, right? So this is 1 plus 2. So I want you to pay attention to this. This is very, very important. So this comes because of this, and this comes because of this. Okay. So this is just convention, right? I mean, you have to. That's the way you. Suppose I were to ask you to calculate the determinant of a 10 by 10 matrix, you can write an algorithm in a computer using the Laplace expansion. Okay, there is no other way. This is the fundamental definition of a determinant. Okay, so this is nothing but this is A12. Now, by definition, determinant of a single scalar is just a scalar number, and oh, I'm sorry, I forgot to write this is A32, right? I forgot to write this, and determinant of A32 is A32. Now again, this is where the notation can cause confusion, right? The reason is, as I told you, if A32 is minus 3, then this is just minus 3. This is not modulus. Okay, this is not modulus, this is determinant. So I have to simply take whatever that entry, whatever that element is. So this is A12, this is minus 1 squared, which is plus 1, A33. This is minus 1 cube minus 1, so there is a minus, A13, A32. So this is how one writes down the determinant of a higher order matrix. Here I showed with respect to a third order matrix and then second order, but you can keep doing this for any higher order matrix because the definition is very general. Okay, so the key thing that you should remember is the determinant of minus 2 is minus 2. This is not modulus. Unfortunately, the notation can be confusing sometimes, right? And this is not 2. Okay, this is not correct. This is correct. You have to simply take the same number. Okay, so if you do this, then you will get the usual expansion for the determinant of this this whole thing. So you can similarly find out what these are, and you will get the same answer, and you will get the answer that this is A11 times A22 A33 minus A32 A23 minus A12 times A21 A33 minus A31 A23 plus plus A13 times A21 A32 minus A31 A22. I've just shown here this first part, which is what you find here, right? The other two contributions can be easily identified. There is no confusion. The key idea is the key use of the Laplace expansion or the fundamental definition of the determinant is that it can apply to any n by n square matrix. You keep successively going down to n by n to n minus 1 by n minus 1, and you keep doing this all the way up to 1 by 1 matrix, that is a scalar, and you recursively apply the definition. Okay, that is the idea. Now there are some properties of definition of the determinant that you may be familiar with, but it is good to recap. Okay, firstly, the determinant of transpose of a matrix is the same as the determinant of the matrix. Okay, the determinant of the Hermitian conjugate of a matrix, if I have a matrix with complex entries, okay, A dagger, what is A dagger? It is A transpose whole star, right? This is the Hermitian conjugate. Okay, this is nothing but, so what is this? We can readily identify ourselves what this is. This is nothing but A star whole transpose determinant. That's the definition of A dagger. This is dagger, right? This is nothing but, I know that the determinant of a transpose of a matrix is the same as the determinant of the matrix. That is from the first relation. So this is nothing but determinant of A star, the complex conjugate of A, which is nothing but the determinant of A complex conjugate. For example, if I have a matrix 1 0 0 I A, then what is A star? A star is the complex conjugate 1 0 0 minus I. What is this determinant? It's I, right? Let's write det A is I. Here det A star is minus I, right? 1 times minus I minus 0. So the determinants are complex conjugates. Okay, so the determinant of the Hermitian conjugate of a matrix is the complex conjugate of the determinant of the matrix itself. Okay, now there are other properties. If two rows or columns are interchanged, of a matrix are interchanged, then the determinant of the matrix changes its sign. Okay, but magnitude remains same. Okay, now suppose I have all the elements of a single row or a column are multiplied by a common factor. Suppose I have a matrix, let's say this is lambda a21, lambda a22, lambda a2n. All the other things don't have, okay, a and 1, right? But only one row or a column is multiplied by the same number. Then the determinant of this matrix is lambda times the determinant of the matrix without the factor. That is, this is, let me just write it properly. Determinant of simply a11, a12, a21, a22, an1, an2, so on. Okay, right. So if all the rows and columns are multiplied by the same factor, determinant of lambda 1, a11, lambda a22, lambda a23, lambda an1, all the rows of this matrix and so on, then the answer is this is lambda to the power n times a determinant a11, a12, a21, a22, an1, an2. Okay, now if two rows or columns are identical in a matrix, then its determinant is 0. Okay, or if they are multiples of one another, not just identical or multiples of one another, then it's very easy to show that the determinant of such a matrix is 0. Okay, so the other property is determinant of A is unchanged in value if you add one row or a column to any of the other rows or columns, or you multiply a given row or a column and then you add it to another row or a column, then the determinant will not change. Okay, if one row or column is added to another. Okay, finally, determinant of A times B is determinant A times determinant B, that is equal to determinant of B times A. Even though AB is not equal to BA in general, you know that matrix multiplication is not commutative, but determinant of AB is determinant of BA. This is something that's interesting about matrix multiplication. Okay, now we'll come to inverse of a matrix. Okay, if I have numbers, let's say P is equal to A times B, okay, then B is written as in normal numbers, right? A upon P, or you can write it as P inverse A, okay, right? B is written as P inverse A, okay. Now P inverse is called the multiplicative inverse of P, because if I multiply both sides of this expression, P inverse P is P inverse, right? Let's see. So I got it wrong here, so that's why. So B is basically P upon A. P is A inverse P, right? So A inverse is the multiplicative inverse of A. If I have 3, then its multiplicative inverse is 1 over 3, so that you get 1. But what about matrices, right? If I have a matrix P which is written as a product of two matrices A and B, right? You cannot write B is equal to P upon A, just like you do it for numbers, right? You have to define what is called the inverse of a matrix. The inverse of a matrix is if AB is equal to P, then an inverse of a matrix is defined such that if I have a matrix A, if I multiply by its inverse, you get the identity matrix. What is an identity matrix? It has ones only in the diagonals and then zeros elsewhere. Okay, all the diagonal elements have 1, all the other elements are 0. That is called the identity matrix. Okay, so if A inverse, this is also equal to A inverse A. This is the definition of inverse of a matrix. So how do I find B? So I have to simply multiply, pre-multiply by A inverse. Okay, now A inverse A is I. Okay, but I times B is B. We have already seen that. That's the definition of an identity operator, right? It's A inverse multiplied by P. Okay, so this is the importance of inverse. That is, if I have a product of two matrices to give this, if I didn't know what this matrix was, I have to find what this matrix is such that if I multiply it by A, it gives P, then that matrix is obtained by multiplying A inverse and P. Okay, and where A inverse is the inverse of this matrix A. Okay, right. So how do you find the inverse? The next question is obviously, how do you find the inverse? Okay, how do you calculate the inverse, right? So first of all, inverse is again defined only for square matrices. Okay, n by n matrices. What is the definition of inverse? The ikth component of A inverse is the transpose, ikth component of the transpose of the cofactor matrix, okay, upon the determinant of A. But the transpose ik is nothing but cki upon A. Okay, where cki is the cofactor of aik. Okay, so this is the way in which you calculate the inverse of a matrix. How do you know this is correct? You can sort of roughly prove this. So the only way you can prove is you can find out what is A inverse A times ijth component. That is nothing but summation over k A inverse ik akj. But I know what is A inverse ik, summation over k. This is nothing but cki by A akj. Now we can show that from the definition of a determinant, if you remember the definition of a determinant, you got the product of an element and its cofactor. This is precisely the same, right? So you will know that you can show that if you take k is equal to 1, you get c1 1, and then a1. So suppose I take I is equal to 1 and j is equal to 2, then you can show that only those factors that contribute to the determinant are non-zero and all the others are 0. So you can show that this is nothing but delta ij. So this cancels off. So A inverse A ij is delta ij. Okay, so that's why this is indeed the determinant. So in order to find the determinant of a matrix, all you have to do is to find the cofactor. If you want to know the ikth element of the inverse of matrix A, find the cofactor of the kith this is ki, the element of A, and then divided by the determinant of A. Okay, so this immediately tells you that inverse is not defined. If determinant is 0, then inverse is not defined. We say that if the determinant of a matrix is 0, the matrix is termed to be singular. Again, please note the different context in which the phrase singular is coming in. In complex analysis, singularity and singular has a certain meaning. In linear algebra, determinant has a matrix is termed singular if its determinant is 0. So determinant of a matrix is given by the transpose of its cofactor upon A. Okay, determinant of inverse of a matrix. Okay, now there are some readily derived corollaries which I will not spend much time on. First of all, you can show that A inverse whole inverse is nothing but A. Secondly, we can show that A transpose whole inverse is A inverse whole transpose. That is, the inverse of the transpose of a matrix is the transpose of its inverse. Similarly, the Hermitian conjugate inverse is nothing but the inverse of a Hermitian conjugate of a matrix is the Hermitian conjugate of its inverse, and AB whole inverse is B inverse A inverse, and this applies not just to two products of two matrices A, B, C, so on up to G is G inverse, so on up to B inverse A inverse. Okay, all these are very readily proved. Now we know that A inverse is I, so determinant of A inverse is determinant of I. Now determinant of identity matrix is 1. Identity matrix, you remember, is just 1 0 0 0 1 0 and so on. So determinant of identity matrix is simply I. So determinant of product of two matrices is the product of the determinants. So this is determinant A times determinant A inverse is equal to 1. So determinant of A inverse is 1 over determinant of A. Okay, so these are some of the properties of determinants of a matrix. Okay, so the last topic that I'm going to discuss today, in this module, is the rank of a matrix. This has a lot of significance in the solution of linear equations. Right now we will understand what a rank is, and we will come to how to use or how to find out the implications of rank a little bit later when we discuss solution of linear equations. A rank of a matrix is again a single number that corresponds to a matrix. Okay, but unlike trace or determinant, rank is also defined for non-square matrices. In fact, it is more relevant or appropriate for it. You can define it for square matrix as well, non-square matrices. Okay, suppose there are two equivalent definitions of a rank. So definition 1, suppose I have an m by n matrix, that is, you have m rows and n columns, right? That is the meaning of an m by n matrix. So I can think of this matrix as a collection of n column vectors. Okay, so So instead of so there are n column vectors, 1 2 3 and so on up to n. Okay, the first column, second column, third column and nth column. Okay, so what is the rank of A? So you can think of these column vectors as v1, collection of v1, v2, vn, and each of this vector v1 is a vector which has m rows and one column, right? Because the order of there are m rows, so each of this is an m by 1 vector. The rank of a matrix is the number of linearly independent vectors in the set v1. So you have a bunch of column vectors, right? We have to find how many of them are linearly independent, and that will be the rank of the matrix A. Okay, so in some sense this also tells you the rank of a matrix equals the dimension of the vector space spanned by the column vectors. Okay, you can also consider the number of linearly independent vectors instead of thinking of this same matrix. Let me just take a minute to instead of thinking of this matrix as a collection of n columns, you can think of it as a collection of n m rows, right? Where each of this is a row vector. Now you can also, the same rank is also the number of linearly independent vectors, row vectors in the set w1 wn. Okay, so and rank is unaffected by simply exchange of two rows or two columns of a matrix, or if you multiply a row by a scalar number and so on. Okay, and you can also add a constant multiple of one row and add it to another row, still the rank remains the same. The second definition of a rank is that you can form a submatrix. Let's first understand, you can form a submatrix of a matrix, given matrix A, by ignoring one or more rows or columns. Okay, the rank of an m by n matrix is the size of the largest square matrix whose determinant is non-zero. Okay, so even though you have an m by n matrix originally, this matrix will have an r by r submatrix where r is the rank, whose determinant is non-zero. Okay, but if you consider another submatrix of dimension r by 1 plus r by 1, its determinant will be 0. Okay, so that means that the rank of the matrix A will be R. Okay, now for a square matrix, okay, before I do that for a square matrix, we can in general say that rank of an m by n matrix R is less than or equal to the smaller of m or n. Okay, for a square matrix, okay, which is n by n in general, if determinant of A is 0, so or determinant of that matrix is 0 unless R is equal to n. If R is less than n, that means the determinant of A is 0 or A is singular. Okay, so the rank of A is sometimes denoted as RA. This is the rank of A. Okay, so the rank of A of a square matrix will be so the determinant of the square matrix will be 0 unless its rank is equal to its order. Okay, if the determinant of an n by n matrix is 0, then rank is definitely not n, it is something smaller. Okay, so I think I'll stop here for this module. In the next module onwards, we will discuss special square matrices such as symmetric matrices, orthogonal matrices. There is a whole bunch of matrices, square matrices, which have very special properties, and those have a lot of implications later on when we go into linear vector spaces and function spaces. So we'll stop here, and thank you for your attention.